Today we're going to talk about chapter 13 and 14, which is on two-sample and chi-square inference. So 13.1 is on comparing population means with two samples. So the goal of this is to compare the responses of two treatments or compare the characteristics of two populations. And we're going to use this if there's a separate sample from each population or treatment. And just as a reminder, we're going to use z-test or interval when the population standard deviation is known and t when it is not. So the conditions for these are going to be that we need an SRS from both populations. For normality, we're going to need the combined sample size of the two samples for z-test or interval to be greater than or equal to 15. And for t, we're going to need it to be greater than or equal to 30. And for me, I like to remember that the t has to be larger because since the population standard deviation isn't known, we need a larger sample size or aggregate sample size in this case in order to be sure of our distribution. And then lastly, the samples must be independent, or the populations for each sample must be at least 10 times the size of their respective samples. Here we have the test statistics and intervals written out. So the basic idea behind these, remember, is that we're taking, for a z-score or t-score, we're taking the statistic and subtracting the parameter and dividing it by the standard deviation, or in this case, standard error. So the only difference is that since there's two samples, we're finding the difference in mean. So we're just going to have x bar 1 minus x bar 2 minus the difference in parameter, which because our HO is going to be that they're equal to each other, they're going to be 0. So we don't even need to write that when we write out our formula. And then we're going to divide that by the standard error, which is sigma sub 1 squared divided by n1 plus sigma sub 2 squared divided by n sub 2. And then the only difference with the t statistic is that since we don't know the population standard deviation, we're going to replace that with s, which is the sample standard deviation. And then a couple quick notes at the bottom. Make sure that on your calculator, you do not pull the data because that is an option when you run the tests. But we don't want to do that. And then for degrees of freedom, that's going to be given by the calculator. Remember that it uses that crazy long formula that we don't need to know. So you can either just use the number given by the calculator or use the smaller sample and subtract 1 from that. And then for the confidence intervals, it follows the same pattern as any of the other confidence intervals, where we take our sample mean and then add or subtract our z star or t star, and then times the standard error. And then for the confidence intervals, make sure you guys discuss whether or not 0 is on the interval and the significance of that. So we're going to walk through an example problem right now, and then you guys will get some practice to do. So the question posed is there a difference between normal pencils and mechanical pencils? In order to find out if there is a difference in how long they last, we take a random sample of lifetimes of normal pencils in minutes and another random sample of mechanical pencils. Run a test of significance at alpha equals 0.1. So here they give us data. And what clues us into using a two-sample t-test is first that they don't give us the population standard deviation, so that rules out z. And then we can rule out using a one-sample matched pair t-test because they state in the question that they're two separate samples and the sample sizes are different. So we definitely have to use a two-sample t-test. So for our first step, we're going to state that and then state our HO and HA, which is that mu sub 1 is equal to mu sub 2. And then for the alternative hypothesis is that mu sub 1 does not equal mu sub 2. And then don't forget to define your variables at the bottom. Step 2, we're going to check our conditions. So both sets of data need to be from SRS, and that is stated in the question. And then for the normality condition, because n sub 1 plus n sub 2 does not exceed 30, we must use the box plots for them. And so plugging the data into the calculator gives these box plots. And since there aren't any apparent skews in the box plots, we can go ahead and continue doing the problem. And then lastly, are the samples independent? So we must assume that the samples are taken from populations greater than 60 normal pencils and 50 mechanical pencils. Step 3, we're actually going to do the test. So first we write out our statistic. Then we can plug it into the calculator, which will give us the output on the right. Make sure you use the two-sided test, because the question was just asking for a difference in the types of pencils. And then that'll give us the following results. So don't forget to draw your graph. And then once again, since it's two-sided, we're going to shade on both sides. And that'll give us a p-value of 0.0391 with the degrees of freedom stated there. Lastly, for our conclusion, since the p-value of 0.0391 is less than alpha equals 0.1, we reject HO and conclude that the true mean lifetimes of the normal pencils and mechanical pencils is different. And since the question was just asking if they're different, we don't have to say that one lasts longer than the other. We're good there. So now we're going to talk about 13.2. So 13.2 is on comparing two population proportions by looking at the difference between sample proportions. So conditions, once again, both data sets must be from an SRS. For normality, we must have at least 5 successes and 5 failures, and that's found by doing n times p and n times 1 minus p, so we have to do that for both samples. And then lastly, the observations must be independent, or the populations must be at least 10 times their sample size, which is the same as before. So the test statistic and confidence interval aren't fully written out here because they're basically the same. All that we're going to change is replace some x bars for p hats, because we're trying to find the difference in proportions this time. And then one note to make for the standard errors, this comes directly from the pink packet, so it's easy to remember. But the only difference, and something you do want to remember, is that the test uses P sub C, which stands for combined. And we use that to find that we aggregate the data by adding up our X values and dividing it by the total trials across both samples. So we use that for tests, but then for intervals, we just use p hat sub 1 and p hat sub 2. And then once again, for our intervals, we're going to want to discuss 0 being on or not being on the interval and the significance of that. So 13.2 example, the question is, has the percentage of MHS students getting into Ivy League schools increased? Random samples were taken and the statistics are below. Construct a 90% confidence interval. So we have the results here. And so step 1, we're going to state it. So 2 proportion Z interval for the difference in proportions and 90% confidence. And then we're just going to define P sub 1 and 2 as the true proportions of students from MHS accepted to Ivy League schools in the 1990s and 2000s. Step 2, we're going to check our conditions. So both sets of data are from an SRS because that's stated in the question. For normality, we're just going to use our little formulas here to find that there were 15 successes and 69 failures, and then 21 and 85 in the second sample. And then for independence, are the samples independent or the 10% rule? That's unknown, so we're going to need to make sure we state that in our conclusion in step 4. Step 3, we're going to state our interval here. If we calculate this by hand, first we're going to use inverse norm of 0.95 because we're doing a confidence interval for 0.9. And then since it's a z-score, we're going to use a mean of 0, sorry, and a standard deviation of 1. And then after we use that, we'll use the formula to the left. Or you can just plug it into the calculator if you have a 2-prop z and option, which will give the confidence interval here. And then for step 4, our conclusion, we are 90% confident that the true difference in proportion is on the interval negative 0.1132 to 0.07416. There are between 11% more and 7% less students accepted into Ivy League schools from the 1990s to the 2000s. And since 0 is on the interval, we can conclude that there's no difference between the proportions of students accepted in the 1990s to the 2000s. And then we're just going to add that this is valid only if all conditions are met. So now that we've looked at chapter 13, you guys can do some practice problems.